All right, I'll begin with a word of prayer. Like everybody is here who's going to be here. So, Heavenly Father, we thank you for this day. Thank you for the spring break, which has already started. And help us to have a good class today. Help us to understand a little bit more about your creation together, and just help me to not be confused. Amen. So, I have some stumbling blocks with this material. Like, I'll just admit it. Like, I get twisted on certain things in here. And but anyway, I have something for us to look at here in a bit. But before I do that, I just want to write down the equations here. So what we found, right, were the Lorentz transformations. Right, so if you've got a frame of reference with, say, you have an S coordinate system, and then you have another one. So we use x prime for the moving coordinate system typically. And suppose that's moving with velocity v with respect to the unprimed frame. And so for the sake of discussion, let's call the unprimed frame the lab frame, and let's call the prime frame the moving frame for the sake of discussion here. And if that's the situation, then we derived last time, right, that x prime is equal to gamma times x minus vt. And we also derived that t prime is equal to, let's see here, gamma times ct minus vx over c squared. All right. What I didn't mention, but I should also, is that y prime is equal to y and z prime is equal to z. So if we continue this to, 3 dimensions, then nothing happens. Nothing happens to y and to z. All right. And let's see here. We derived the velocity transformation, right? What did we find? We found that if you were going velocity u in the moving frame, right? So if, let's see here, if dx prime dt prime was equal to u, let's say, goodness, I might even call it u prime, but anyway, I didn't last time, so let me just leave it as u. Then what was the corresponding dx dt? We worked it out. So what we did, remember, we just literally thought of these, in terms of very small increments of x and t, and we used the differential notation. We basically divided these two equations, and what did we get out? Do you guys remember? What we got was u, let's see here, u plus v, right? Oh, goodness. Oh, see, this is the problem. Well, it's not a problem. It's just, so to do the calculation again, if I was to, this wouldn't be helpful here, right? What do I need? I don't need these transformations. I need the inverse transformations. What are those? So vice versa, like if you have x, you can relate it to x prime like this. X is equal to gamma times x prime minus vt prime. But not a minus, but a plus, because the v reversal. So if you think about the perspective of the moving frame, right, the lab frame is actually moving with velocity minus v in the other direction. So it's the same equations, it's just we've replaced v with minus v for the other way around. So actually it would be this one that I should use to derive this here. I'm not entirely sure I did that last time. Well, anyway, let me not try to dissect last class in the middle of this. So essentially, you just put that into here, right? So we have gamma times dx prime plus v dt prime divided by gamma times c dt prime plus v over c squared dx prime. And then if I just sort of formally divide that, well, the gammas cancel. And if we divide by dt prime, we get dx prime dt prime plus v divided by what? Well, c plus v over c squared times dx prime dt prime. Okay? And then that gives us, what does that give us? That gives us u plus v over what? Man, something's askew here. Well, this is dimensionally inconsistent. You guys, tell me what's wrong with these equations. You don't need to be a relativist. Like week 1 in this course would tell you what's wrong with that. Not that I emphasized it much, right? Certainly a shortcoming of my pedagogy this semester. A lack of an emphasis of dimensional analysis. But look, this, to quote my community college professor, this dog will not hunt. You can't have a C here and no C over here. That's like adding, you know, a dog to a cat or something. It's just nuts. So this gamma, remember, is dimensionless. Gamma here, the formula for it, we found 1 over the square root of 1 minus v squared over c squared, right? So in short, this is a typo. So just erase these, all right? Let me just erase them from the record, okay? There's no c here, and there's no c here. That's what I should have. And as such, there's no c here, which makes this not a c, but a 1. Right? And so what's the formula? Well, the formula here is 1 plus, and what is dx dt? Dx prime dt prime is u, remember? So that's u uv over c squared. All right, so again, this is the velocity in the lab frame that you would measure for something that was moving with speed v, with speed u with respect to the moving frame. So this answers one of your homework problems, right? This is what you should use to do which homework problem? Give me a second here, I'll tell you which one this is relevant to. This is the formula to use. I believe this is problem 76. Suppose a space train going at velocity c over 2 with respect to frame s. Then the space train has a bike rider who rides on the train at velocity v2 equal to c over 2 with respect to the frame of reference of the train. What's the observed velocity of the bike with respect to s? So you got to do some, like, you have to interpret this appropriately. It's not the same letters, right? But it's essentially that formula with v equal to c over 2 and u equals to c over 2. I think the right, I think it's just think of u being v2, and I think that's it for problem 76. Okay, so enough about that. Thank you. So any questions? Yeah.
To be clear, v is the speed of the frame of reference. dx dt is the speed of the object in relation to s, and dx prime dt prime is the speed of the object in relation to s prime.
Correct. Yeah. So the speed of the object with respect to s prime, or the velocity with respect to x prime, right? It's the x component of the velocity, to be more pedantic, right? Whereas the x component of the velocity with respect to s is this. That's what this is. Yeah. And so again, just to emphasize, how does this go in the Newtonian case? It's very boring, right? In the Newtonian case, how did we derive this? Like pretty much we just had r prime is equal to r naught plus tv, something like that. And essentially in the Newtonian case, this whole denominator just drops out and it's just u plus v. That's what happens in the Newtonian case. The velocities add. Hey, while we're doing this, what's the rule for the transverse velocities? Right? So if you want to think about the other coordinates like y and z, right? So I'm assuming at the start that the, let's see here, what would, I'm assuming dy, dy prime dt prime and dz prime dt well, let me behave. Let me not go down that. I was thinking we could derive the other velocity rules here real quick. I might be able to do that. Well, here, let's try it. What would dy dt be? It would be what? Dy prime? Dy is, dy would be equal to y prime, right? What's dt though? Well, dt is here, right? It's gamma times dt prime plus v over c squared dx prime, yeah? And so if you divide this relation by dt prime, what do you get? dy prime dt prime divided by gamma 1 plus v over c squared dx prime dt prime. So this is a kind of weird thing, right? You have the y velocity in the y prime velocity is divided by gamma times 1 plus uv over c squared. So even though there's no motion in the perpendicular, like in the y direction, right? The velocity transformation is just in the x. It still makes the velocities transform in the transverse directions, and according to a different rule. So here you end up dividing by gamma and that, because the time is not the same. So that's the larger issue here is, and this is really weird, is if we compare two events, right? From, say, the frame of reference, the lab frame versus the other frame, the times disagree, right? There's no notion of simultaneity. Let me look at some space-time diagrams with you. Oh, before I do that, let me clean up these equations just a little bit. So you see, this is not the best way of looking at these equations. So the best way of looking at these equations is to look at it this way. We've got ct prime is equal to, what is it? Ct prime is equal to gamma times ct, all right? And then you've got minus v over c times x. Do you guys see that? So what I did was I took this equation and I multiplied by c, all right? I took the equation for t prime and I multiplied by c. It looks like this, right? On the other hand, x prime is equal to, what was it, gamma times x minus vt, right? Vt. And, but I'm going to rewrite that as v over c times t, all right? And then we've got y prime equals to y, we've got z prime equals to z, if we want to think about it four-dimensionally. And so what usually is done is you let x upper 0 equals to ct, you let x upper 1 equal to x, you let x upper 2 equal to y, you let x upper 3 equals to z. These are the usual space-time coordinates. And these space-time coordinates are made in such a way that they're all of the same dimensions, right? Basically multiply the time by the speed of light so that it has units of length, right? Now they're on an equal footing, so you can kind of understand the Lorentz transformations in a more, more beautiful way. And so in terms of this then, what would these equations become is x0 prime equals to gamma times x0 minus beta x1. And this one becomes x1 prime is gamma times x well, let me write it this way, minus beta x upper 0 plus x1, and x2 prime is just x2, and x3 prime is just x3. Now, some of you are taking Math 221, yeah? Surely someone in here is taking either has taken 221 or is about to take it. No? Am I totally off my rocker? No one knows what a matrix is? No one ever saw a matrix in high school? You know what a matrix is? You're like, eh. Okay, well, that'll work. That's all I need. I just need enough. So it's really just a box of numbers, right? So you can rewrite these as a matrix like this. And the matrix is this, gamma minus beta gamma, minus beta gamma, gamma, and then you got zeros. All right. And furthermore, you can introduce what's called the rapidity. So you can, the rapidity is the gamma is the hyperbolic cosine of the rapidity. Beta times gamma, it turns out, is the hyperbolic sine of the rapidity. The rapidity itself is defined by this. The tangent of the rapidity is equal to v over c. So rapidity, I'll write that down. Rapidity is defined by the hyperbolic tangent of the rapidity is equal to the velocity divided by c. This is interesting because in terms of the rapidity, and I was supposed to have a matrix multiplication here. Sorry, guys. My bad. So it's this 4 by 4 matrix times that 4 vector, right? And so if you rewrite this matrix in terms of, hyperbolic sine and cosine, it's like this. Cosh phi minus sinh phi, cosh phi, and then 1's down here. So this is what's called a Lorentz matrix. And part of the reason I mention it is just so you have a better appreciation of why we study hyperbolic cosine and sine in calculus. This is the connection of sine and cosine. Well, this is how cosh and sinh appear in physics, is they appear in terms of the components of the Lorentz transformation, among other places. And you might say, well, who cares? Well, interesting thing, if you study how velocities add instead in terms of rapidity, it turns out that the rapidity, like if I defined, let's say, tangent of phi 1 equal to v over c, and if I had tangent of phi 2 equals to u over c, all right, then the if this, I need to give this thing a name. Let me call this Bob, all right? Then the tangent of phi 1 plus phi 2 is equal to Bob over c. In other words, the rapidity of a moving object with respect to the lab frame is equal to the rapidity of the moving object with respect to the moving frame plus the rapidity of the frame of the moving frame itself with respect to the lab frame. In short, rapidities add. So if you study rapidity, it goes back down to like the Newtonian idea of you just add them to find the velocity. And through the magic of the hyperbolic tangent, things never get past speed c. Essentially because that hyperbolic tangent has that horizontal asymptote of 1 as you go on out. All right, anyway. I had a point to all this. So there's an interesting thing we can calculate, right? In terms of these coordinates, something that's an invariant between both frames. So if you calculate, I've got enough space, I don't guess I do. So, all right. If you have two standard coordinate systems, right, in terms of rectilinear perpendicular axes, right? And you measure the distance between 2 points, right? Right? And I measure the distance between 2 points in another coordinate system, which is also set up with regular perpendicularly related axes, right? And suppose that these two coordinate systems are moving with, constant rectilinear motion with respect to each other. What can you tell me about the measurements? We should both agree that the distance between the 2 points is what? The same, right? Like Euclidean distance between points is an invariant of Euclidean geometry. There's something similar here that you can find. It's called the invariant interval. It turns out that you can calculate that if you look at, let's see here, minus c squared t prime squared plus x prime squared plus y prime squared plus z prime squared, all right? If you plug in the Lorentz transformations, all right, and you work those out, it all cancels out. And it simplifies down to minus c squared t squared plus x squared plus y squared plus z squared. And you can look at this infinitesimally as well. So anyway, this is the so-called invariant interval. Sometimes you might put like change in t, change in y, x. You can put changes in here if you like. So anyway, that's the invariant interval. So that's useful for solving problems because you can compare two events in terms of one frame reference versus another by saying, well, they both have to have the same interval. So that allows you to figure out how the unprime coordinates are related to the prime coordinates for a particular problem. And so this is kind of like, okay, so the a more elegant way of writing this is as follows. You can really look at this as, well, I don't know if that helps you or not. There is a problem in your homework which is roughly about this. Let me see if I've said enough yet. So problem 84 is more or less about what I'm talking about right now. So yeah, problem 84, I basically ask you to show that that's true in a different notation, but that's what 84 is about. So I define, in problem 84, I define G of V bar W bar equal to minus V naught W naught plus V1 W1 plus V2 W2 plus V3 W3, like that. So these are what are called four vectors. These are four vectors, which is to say that they're vectors in space and time. And so you can calculate that let's see how to say this. So I think of V bar, the way to think of a four vector, for example, was like a displacement in space and time. So you can take the difference of events. So I could take like event 1 minus event 2. So an event is a time and a location. So think of it's like a four-dimensional time with three spaces, right? Well, c times time. And so if you think of that as one, and you think of, you could also write that in terms of, well, let me just shut up. If I say more, I'm just going to end up solving the homework problem. It won't be interesting. So, all right, let me get back to track here. All right, so obviously I don't have time to derive everything today, so I'm just going to tell you some things at this point, and hopefully that'll be okay with you. So to properly do special relativity, we need, I don't know, probably about I don't know, at least a third of a semester, something like that. But I had a course in it. We spent a whole semester looking at these things, and I think that's healthy. We don't have such a course here, but we do have the modern physics course, right? So you probably spend a couple weeks in there. And so I think you might do a little bit better than I'm doing at the moment. But let me just get to the main points. So to study, you study proper time. Proper time tau for a particle. So the way to think of this is if we think about our space-time diagram. So here's the time, and here's space, let's say, right? You can talk about the motion of a particle through space-time, right? And you can draw a picture. And there's some things that I should say here. If I make this CT, that's a little bit better, because if I make it CT, then we have some rules, right? So this is the light cone. So here you have basically CT. Well, let's say here. How can I say it? Slope 1. What is slope 1 here? What does slope 1 mean? So rise over run, what would that mean? Yeah, you want to say that, but it's a little bit upside down, right? See this? So if x is equal to ct, right? If x is equal to ct, you get 1. But my larger point is it actually ends up being 1 over the speed. The slope is 1 over the speed because we're putting time upwards. But you're right. I mean, it is related to that. So here would be like the velocity equals to minus c is this line. All right. So if your particle, you can draw what's called a world line. So if you suppose the particle starts at the origin, all right, then the world line, it can do, it could look like this, for example. Although I have to be careful. Technically speaking, at no point should the line have a slope which is what? Yeah, less than 1. Other way around, because it's all reciprocal. So if the slope is less than 1, that would correspond to it having a speed faster than the speed of light, right? So we can't have that. And the way to think about it then, I don't know if I think I may have failed to live up to my own rules here, but maybe something like this, I don't know. The point is, you could think about the coordinate system that kind of moves with this, So think about this as being like the tau. Tau is the co-moving time to the particle, all right? Anyway, long story short, if you study this, you study something called the proper velocity, all right? So you can define u, let's say mu, equal to dx mu d tau. So this mu is a notation. That's just what I was doing before. I just erased it, but that's like 0, 1, 2, 3, those coordinates. So the 0th one is is c times t, right? Then you have space, space, space. And if you differentiate this, so if you think about this, this is the so-called 4 velocity. So what's a 4 velocity? Well, it's something kind of funny, right? Let's see here. As I'll show on the overhead projector here pretty soon, hopefully before I run out of time. Yeah, we're good. There's something called time dilation. All right, so time dilation, in a nutshell, what it says is that, let's see, I'm trying to get it right. Let's see here. So this is going to be, I can write it as a vector like this. What you've got is so I'm getting into trouble here. D of, I guess, ct, d tau. And then you've got, dx d tau, dy d tau, dz d tau. So the 0th component of this is like weird and new. and it works out to gamma. This just turns out to be gamma. I think maybe C gamma in my current notation. And then these ones, basically we have this. Well, it works out to gamma times dx dt, gamma times dy dt, gamma times dz dt. So the for velocity, it's like, to use other notation, it's like this. It's like C gamma, and then you've got gamma times the ordinary velocity. So in the relativistic for velocity, you end up picking up the regular velocity times this gamma factor. All right? And then you define the for momentum. The for momentum is equal to the rest mass times the for velocity. So the way that works out is you've got yourself an m, well, you got m gamma c, right? I feel like I'm missing something dimensionally.
C is in meters per second.
That's right? Okay, cool. Something feels wrong, but anyway, so this, that was the upper mu, my bad. M gamma c. So let me just put it in parentheses here. So you have m gamma mc, and I feel like I'm missing a factor of c or something here at the moment, guys, but let me just stick with it here. Our time is limited. I know you guys want to start your break. So that's what we have. So long story short here, this ends up being what we call the relativistic momentum. So relativistic momentum, like the ith coordinate, well, let me just write. This is a three-dimensional vector. P vector is m gamma v. So the relativistic momentum is just the regular momentum times gamma. Noticing a trend here? So you take the regular thing, you multiply by gamma. That's the relativistic version. All right. Let's see here. Now, the zeroth term here is actually very interesting, and man, I feel like that's missing a c squared. There's like another c that should be here, and I don't remember why. Oh, well, anyway, here's something. It turns out that in this story, if you calculate like the invariant interval for these, that also is something that has to be invariant. So anyway, I think I better not derive things here. I should just tell you the formulas, right? Okay, so here we go. The total energy, and there's something missing in my story at the moment, but I'm just going to have to get over it, okay? The total energy is m gamma c squared. So this is like total energy. And it's, if I was more with it today, I could explain to you how this naturally appears from the study of the for velocity and then the for momentum, okay? Like there's a story to tell here. It's not that complicated, all right? But this is interesting because this m gamma c squared is, well, what is that? Like, let's look at this. So what we're looking at is mc squared times 1 minus v squared over c squared to the minus 1/2 power, all right? Now, you guys aren't here yet. So a lot of you are in calculus 2 right now. You haven't quite got to this, but in literally like a couple weeks, we'll derive something called the binomial series. And the binomial series will tell you that we can expand this, provided v over c is small, all right? So in the limit, if v is much, much less than c, let's say, that makes v squared over c squared tiny, and that makes the following like a really good approximation. In particular, we have mc squared times 1 minus a minus 1/2 v squared over c squared. And then, let's see here. Well, actually, who cares what the next thing is, but higher order stuff, okay? So the things that are things in the dot, 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 they involve powers of v squared over c squared. So the binomial expansion I'm using, guys, is just this. If you have 1 plus u to the k power, it's equal to 1 plus ku plus stuff. Simple as that. It turns out. This is the binomial series, first two terms. In this case, I'm just using k equals minus 1/2, and there you go. And I think to be clear, my u is minus v squared over c squared, right? So I'll put the plus out here like that. Okay, anyway, so there's two minuses, they cancel. What do you get? Well, you get mc squared plus what? What's that? When you multiply it, the c squareds cancel, what you got? The v squared over 2, right? Times the m, so we have 1/2 mv squared. And then higher order stuff, right? What is 1/2 mv squared? It's the kinetic energy, right? What's that other term? See, it's relevant even when we're in the Newtonian limit, right? Even when we have v much, much less than c, this term appears in the energy. And of course, this ultimately is what changed the fate of World War II, right? This is how we found the hydrogen bomb and the rest of it. This is the rest energy of the mass. It's huge. C squared, it's very big. So, this is what Einstein noticed in 1905, that there's this incredible energy that's hidden within matter itself, right? Even changing just a little bit of the fraction, if you guys study chemistry, right? Even in typical chemical interactions, there might be a little bit difference in the mass before and after, and it translates into huge energies in terms of the chemical realm, right? That little difference in mass translates into huge amounts of energy. So, or huge amounts of energy. I think that's it for the formulas, unless I'm forgetting something. I need to tell you about time dilation and length contraction, so I'll do that here just a second. But to solve the problems about events, you just have to use these Lorentz transformations to go from one frame to the other. You just plug the data that you're given into these and work it out. That's what you have to do for problems. Let's see here. I'll get to it eventually, guys. 80 and 81, in both of these, I give you specific, values for events in terms of one frame of reference, and then ask you to find them with respect to the other, right? So either you're going to use these equations or those equations in context, right? Those are the Lorentz transformations. All right. Any questions? Yeah.
Is that total energy the relativistic kinetic energy?
The relativistic kinetic energy. So it's kind of slippery, but so that's the relativistic kinetic energy is defined like this. It's equal to gamma minus 1 mc squared. This is the relativistic kinetic energy. Thank you for that question. So all that's really doing is just saying that everything in that formula in red I wrote right above it is kinetic, except for the first term, which we're calling the rest energy. In some sense, this is really just a definition. But it's a reasonable definition in that this formula reduces to 1/2 mv squared, and the limit v is much, much smaller than c. So it's not, it's not insane. There's so many things to say about special relativity, so many interesting things. Here's one. If you study circular motion, what do we have for circular motion? How's it go for us? There's no homework problem on this, so this is just for fun. But for us, mv squared over r is equal to the centripetal force, right? Fun fact that I did not learn this as an undergraduate personally. despite the fact I spent a lot of time in relativity as an undergraduate. there's a gamma. I think it's there. Don't quote me on this. It's either upstairs or downstairs, but there's a gamma that appears in the relativistic version of the centripetal force problem. So the discussion of how Newton's second law gets modified in special relativity is more complicated. It would take me a while to do it justice. Now you might wonder how I learned about this. Well, I learned about this when I took my qualifiers in physics. And I only got half credit for the problem because I didn't know about that. And that's why I'm only a mister in here and not a doctor, right? Because I passed the qualifiers at the master's level when I took them. And I did the best the first time I took them, all right? And then every time I tried them after that, they got worse. No matter how much more I studied, like, it just got worse. That's not how it's going to be for you in this course, though, don't worry. All right, so where was I? Let me, and I will, of course, post this in, you know, what's it called there? The Canvas, right? A little bit later today, hopefully. So these are, what you're looking at here is a kind of complicated picture. And let me try to explain what's going on. Oops, wait a minute. What's going on here? Whoa, dude. This is weird. I didn't know that's possible. How did I do that? Huh, that's funny. All right, there we go. I had the camera on like 90 degrees separate, so I have no, I don't know, whatever this direction of the motion is. Well, we need some aviation majors in here so they can tell me if it's yaw or pitch or whatever. Let's see here. It's pitch? Okay, cool. So this is a picture. So what you're looking at is, I know it's hard, it's busy. All right. I'll also send you a link to a LaTeX document of this where the one is blue and the other is black. I don't have a color printer. Sorry. Right? Not here anyway. So you can actually adjust. This is done for the speed of light being, the speed of the moving frame being half the speed of light. You can adjust that in the LaTeX code and make it for other speeds if you want. And you can also adjust the number of boxes. It's pretty easy. I did it. So anyway, so what you're looking at here in the straight vertical ones is the lab frame. The tilted one is the moving frame. And the thing is, the way this diagram works, you can read the coordinates from either frame of reference at the same time. And I mean at the same, that's, man, the language breaks down here. I don't mean the same time. I mean at once. That doesn't, See, Newtonian thinking is, it's all in our language. It's, man. So my point here is for time dilation, what you do is you start with two clocks, they're synchronized at the origin, and then they go off, all right? The one goes moving in the moving frame, the other one, it stays put, right? And then you can compare times later. So here you have the clock that is moving, you know, it goes to say time, oh man, seriously? Well, that's aggravating. That's the wrong one. That one's wrong. I did this twice. That was my mistake paper. So that's how today's going for me. Great. But anyway. So here, maybe I can redeem it with this one. This here is the this red line here. You could think of as the distance in the moving frame, right? And how do you measure lengths? Like if I'm going to measure the length of this markers, how do I do it? I measure it at the same time, right? That's the part of the deal, right? When we measure length, we measure the, you know, how far it is from here to here at the same time in my frame of reference. That's how we define length in a given frame. So if I'm going to calculate the length of the rod that's moving, if I'm going to calculate that length with respect to the lab frame, I end up calculating this green distance right here. Because this, you see this, the rod is not moving in the lab frame. Like excuse me, the rod is moving with the lab frame. So it moves up to here. And in the lab frame, you're measuring the length of the rod at the same time. So you measure the shorter distance because that's the distance that you measure at the same time. Now, of course, from the perspective of the moving frame, the lab frame is measuring the distance of the rod at different times, and that's why it's not measuring the same length. Right? So there's always this kind of back and forth. Nevertheless, these are not just apparent differences, these are measured real differences. Let's see if rats. Well, I'm sorry, guys. Listen, I really wanted to, I spent 2 hours making that picture, only to scan the one that was wrong. Oh, that's aggravating. So my last thing to tell you for today, if I can rotate this thing. There we go. So I've been working on a course in general relativity for a student who's not here. He's at Alabama, but I've been working on it for a while. And I actually just got to my lecture on what's called the Schwarzschild solution, which is the spherically symmetric solution to general relativity in the presence of like symmetric matter. So it's the solution that's relevant to like describe gravity on Earth and things like that. It's approximate. It also is where the black holes come from and all that stuff. But one of the things that pops out of this Schwarzschild solution is this wonderful formula that relates the frequency of electromagnetic radiation with the radius from the center of the gravitating object. So we can compare, so what I'm saying is that if you take light, right, and you emit it from one radius, and then you observe it at a higher radius, the Schwarzschild solution predicts that you're going to measure a different frequency. And the frequency is directly related to how far you are from the center of the gravitation. So like here's the formula. You calculate the ratio of the frequencies. It ends up being the square root of 1 minus 2gm over r1 and 2gm over r2, which approximately is this. If we're away from the event horizon, this is the event horizon, r equals to 2gm. And so what this means is that if you're doing something like, say, setting up a GPS, how does GPS work? Do you guys know? It bounces off satellites, right? And it's based on playing games with the specific frequencies of the transmission, right? Up and down. So like, if the frequency is changing between where the signal's being emitted from the satellite and going to Earth or vice versa, if you don't account for this gravitational redshift, you'd be off by an amount which is appreciable to the technology. So like GPS that you use actually has a general relativistic correction, necessarily so to be accurate. So this is the answer to the other homework problem, but I think it's interesting. There's also a redshift in special relativity there's like a relativistic Doppler effect. That's a different thing. These are competing effects. So let's see here. Yeah, like I said, frequency goes down as the radius increases. So this is a redshift away. On the other hand, if you're I'm trying to think, if your light's going into if you reverse the story, then you have a blue shift, right? Photons falling into a body are blue shifted. Like for example, if you shoot photons into a black hole, they get brighter and higher and higher and higher frequency as they approach the event horizon, so forth. But anyway, that is a story for another class. And I think this should be due Wednesday, just to be friendly. Was that the question?
Yeah, I was going to ask.
Whoa, I'm clairvoyant or something. But yeah, I don't think I'm really going to help you much Monday with this stuff, but I think I've told you enough to do all the problems, all right? So, but anyway, have a good break, guys. I see now my original plan for four lectures on this was more reasonable.